was good. Okay, so we are very pleased to have Professor Zhiwu from Georgia Tech to give an online seminar today. And his title is Dynamic Magneto-rotational Instability. Okay, yeah, I turn to you.
Okay, yeah, I want to thank Changyu for the introduction and the invitation. Okay, so today I will talk about some recent results on dynamic magneto-rotational instability. So this is joint work with Yucong, Wang, and Wenpei. They're both faculty at the Xiangtan University in China. So yeah, let me introduce the model. So this is the so-called ideal MHD model. So it's a ideal MHD system. There's no dissipation. And the domain is a cylinder. So it could be an infinite cylinder. And for the vertical direction, we assume is a periodic. So we choose period to be 2 pi. So this is the domain. And for the ideal MHD model, the standard boundary conditions, the normal velocity, and the normal component of the magnetic field should be equal to 0 on the boundary. Okay, now let's look at a very basic steady state solution of this MHD system. Is the so-called rotating flow with magnetic field. So our velocity field is a rotating flow. The angular velocity is omega r. So the velocity is r omega r is in the theta direction. And our magnetic field is vertical. So it's epsilon times br. Br you can think of is the strength profile. Epsilon is the parameter for the strength of the magnetic field. And we assume B has a positive lower bound. Magnetic field is not 0. Okay, so this is a steady state. We can easily check by plugging into the MHD equation. Okay, now let's look at the stability of this kind of steady solutions. So first, let's recall a very famous result for the rotating flow. In other words, if you don't put any magnetic field, just consider the 3D Euler equation. So this rotating flow is a steady state of the 3D Euler equation. Now, if you look at the axis symmetrical perturbations, there's a very famous criterion by Rayleigh back to 1880s. So you find out if the angular momentum square is a monotone increasing function of r, then the rotating flow is stable. And for axis symmetrical perturbations, it turned out to be necessary and sufficient condition for stability. But for the MHD problem, if you add even a small magnetic field, let's assume epsilon is very small. So if you change the stability picture quite a lot. So actually, we're gonna see even if you let the epsilon tend to 0, in the limit, the stability criterion becomes omega square should be monotone increasing to r. Okay, so if you compare these two criteria, you can see the second one is stronger than the first one. So in other words, if you partial r omega square is positive, then it implies the Rayleigh criteria, but not vice versa. So this tells you, in certain sense, if you let the epsilon go to 0, so this is a singular limit, right? You do not recover the Rayleigh criterion, even if the magnetic field tend to 0. Okay, so a very important example is Kepler rotation. So omega square is equal to a constant over r cubed. So this is called a Kepler rotation. So for Kepler rotation, we can easily check this profile is really stable, but it's not stable according to the criterion partial R omega square greater than 0. Okay, so why this example is important? Yeah, we're going to see this kind of instability. So let's call it MRI, magneto-rotational instability. So this kind of MRI is very important in astrophysics, in particular to the application of accretion disk. And this Kepler rotation is a typical rotation profile in that setting. So that's why, so this is a very important example. Okay, so let's talk briefly about some history of this kind of instability. So this MRI was first identified by two physicists. One is a Russian guy, Velikov, in 1959, and the other one is Chandrasekhar in 1960. They find it at about the same time. So they find that this is a actually they derive this as a sufficient condition for spectral stability when epsilon go to 0. But they didn't prove this. This is also sufficient for is also sort of a necessary and a sufficient condition. Okay, so we're gonna look at the eigenvalue problem in more details later on. And this MRI somehow becomes very sort of catch attention until much later in early 1990s. Barbers and Rayleigh, they wrote a important paper. They find out this instability mechanism actually plays a very important role in the accretion disk around the black holes. They actually use this instability mechanism to explain the turbulence and the so-called enhanced momentum transport around the accretion disk. Okay, so and this MRI actually have other applications in astrophysics. Okay, so that's why it's a kind of a very fundamental instability mechanism if you have a rotation and also magnetic field. Okay, now let's talk about some mathematics. So first, let's introduce a magnetic potential to rewrite the MHD equation. So here we can define the magnetic potential of phi satisfying the following boson type equation, and with this boundary condition. So the boundary condition is determined by the initial data. Okay, so yeah, by introducing this magnetic potential, we can express the R and the Z component of the magnetic field by using the derivative of psi. Yeah, so it's like a it's sort of like the string function for the velocity. So you just take an analog. So this magnetic potential is used to generate the R and Z component of the magnetic field, because the magnetic field is divergence free. So it's also true for R and Z components. They are divergence free. So that's why we can use a magnetic potential to generate it, right? Okay. So this is the magnetic potential. Okay, now if you use magnetic potential of phi to replace the R and the Z component of the magnetic field, but we still keep the theta component of the magnetic field, then we get the following equivalent system. Yes, throughout this talk, we only look at the axis-symmetrical perturbations. Axis-symmetrical solutions of the MHD model. So in other words, all our quantities depends on R and Z. Okay, now the MHD system becomes this equivalent system, this system number 7. Okay, now let's do the linearization. So a first step to understand the stability of a steady state is to look at the linearized equation. So in other words, we look at a perturbation around this steady state. Then we throw it into the nonlinear system and get rid of all the quadratic term and any other higher order terms. Then you end up with the linearized system. So this is a system number 8. Okay, now let's see how we can understand the stability. A common way to look for a unstable mode is to do the separation variables, because here our steady state only depends on R, so you can do the separation variables R and the theta and the Z, right? R and Z. Our solution actually does not depend on theta, it's axisymmetric. So we do these separation variables, we separate R and Z. And let's assume capital lambda is our unstable eigenvalue. Then you plug in this so-called normal mode into the linearized equation. And here, let's assume the magnetic field is uniform for the moment. In other words, the strength profile B is identically equal to 1. Okay, now after some algebra, you get the ODE, second order ODE for the perturbation of the magnetic potential. So this is a second ODE, and the boundary condition now becomes the zero boundary condition at the R1 and R2. So R1 and R2 are the inner and outer boundary of the cylinder. Okay, so looks like yeah, it's just an ODE problem. But if you look at this problem, you see it's a nonlinear eigenvalue problem, because the eigenvalue lambda appears in several places, right? In several places. So yeah, it's not such a trivial thing to solve this eigenvalue problem, to find instability. Okay, so let's look at a so-called local dispersion analysis. Yeah, this has been used by physicists in the literature, because it's difficult to solve this eigenvalue problem. So people try to do some approximation. So a common way is to look for a solution of the form PREIKR. So we assume this KR is big. In other words, we look for a very high frequency perturbation in the R direction. And also the perturbation is very localized at one point, R0. So you look for such a localized and a highly oscillatory mode. Yeah, it's like a WKB approximation in the quantum mechanics. So you plug these answers into the eigenvalue problem, then it becomes the following. Okay, now you take two approximations. First, you assume the radial wave number Kr is sufficiently large. In other words, it's highly oscillatory. The other approximation is your perturbation is highly localized at a point R0. In other words, the support is in a interval around R0, in a small interval around R0. Okay, now if you take these two approximations, the ODE becomes an algebraic equation, right? It becomes the following algebraic equation. So this is also called a dispersion relation. Okay, now the coefficients only depends on the value of your profile at the R0. Okay, now you can use the root formula for the quadratic equation to find the solutions. You get the two roots. Okay, now you take a further approximation. Let's assume the magnetic the magnetic field is very small. In other words, epsilon is small in the following sense. Then you can approximate the square root. So sort of like you do a Taylor expansion. Root 1 plus x is almost 1 plus half x, right? For x small enough. So you take this approximation to only keep the first two terms of the square root. Then you end up with the following approximation formula for the eigenvalues. Okay, so from this approximation formula, we can see if the Rayleigh criterion is satisfied. In other words, if partial r omega square r4 is always positive, it's really stable, and the partial r omega square is negative at a certain point, at a point r0, let's say, then you look at the second eigenvalue. The second eigenvalue, you can see it actually is positive, right? It's positive. Yeah, it's a positive number times epsilon square, k square. Okay, so yeah, if you get a positive eigenvalue, that means you have the instability. Okay, so this is pretty nice, and it has been used quite commonly in the literature. But there's two natural questions. So because we take such a highly oscillatory and highly localized perturbation to get a approximate eigenvalue, so yeah, it's a pretty natural question to ask. Right now, this instability is due to continuous spectrum or discrete spectrum, right? Because we know this kind of localized, highly oscillated perturbations are also used commonly in a finding of a continuous spectrum in fluid mechanics. Okay, so here we want to understand whether or not this is due to continuous spectrum or discrete spectrum. And also, if you have a, in particular, if you go back to the original eigenvalue problem, this ODE star, can we find a really exact solution of this nonlinear ODE satisfying the zero boundary condition? Right? If you can solve this ODE to find the exact solution, that means you find a unstable mode, right? But here, if you take the local dispersion analysis, you can only say you find a approximate eigenfunction, and the eigenvalue we don't know whether or not it's a continuous spectrum or discrete spectrum, right? Okay, and the other question is, can we go from the linear analysis to the nonlinear dynamics? Because for any linearized problem to be useful, it has to predict the behaviors at a nonlinear level. So those are a few questions we need to address. Okay, so before we state the results, let me introduce some function space. So first, let me define this H1 space. So we call it H1 mat, because if you look at this norm, so we define the norm here. So this norm, so this function phi, if you think of it, is the magnetic field. So this is exactly the energy of the magnetic field. Okay, so let's see. Okay, so so this is actually the magnetic energy. So if you think of phi is the magnetic potential. Okay, let me go back here. So that's why we call it H1 mat. So so here think of phi is the magnetic potential. Then this H1 norm is exactly the magnetic energy, at least for the R and the Z components of the magnetic field. So this is one space. We call this space H1 mag. And also, if you impose the zero boundary condition, because for the linear perturbations, our magnetic field satisfy the zero boundary conditions at the two boundaries. So this is our space Z. Then we define these two space X and Y. So X is L2 cross Z, and Y is the divergence free vector field cross L2. So those are some function spaces. Okay, now let's rewrite our linearized MHD system. So this is the system we wrote previously. Yeah, it's this linearized MHD system. So we can write it as a Hamiltonian system. Okay, so by introducing these function spaces, and we regroup the variables. So we put a so here for U2, we group the R and the Z components of velocity field and the theta components of a magnetic field together. So let's call U2. So U2 is in the space Y, in the space Y. And for the other group, we call U1. The first component of U1 is U theta, the theta component of the velocity, plus this function. So this function depends on the steady solution. Partial R omega over epsilon B is U theta plus this function times phi. Phi is the magnetic potential, and the other component is the magnetic potential. So if you regroup these unknowns, then we can rewrite this linearized MHD system as a Hamiltonian system in the following sense. So here, our linear operator is JL. You can decompose it as JL. So J is a anti-self-dual operator, anti-symmetrical operator, and L is a symmetrical operator. Actually, the structure is actually even more special. So here we call it a separable Hamiltonian system, because if you look at the symmetrical part, it's actually diagonal. Okay, so it's actually a diagonal symmetrical operator. And for the anti-symmetrical part, is actually anti-diagonal. So here, B prime is the dual operator of B. So this J is an anti-symmetrical operator, and it's also anti-diagonal. Right? L is a symmetrical and diagonal operator. Okay, so what are these operators? So the operator B is the following operator. Okay, and you can also write down the dual operator of B explicitly. To write down the dual operator of B, we need to use the Rayleigh projection P. So the operator P is the Rayleigh projection from a vector field. So this vector field has two components, R and Z components. So this is a it's like a U R E R plus U Z E Z. So here we project this vector field to the divergence-free vector field. So for the divergence-free vector field, it only has R and Z components. Yeah, you can define such a sort of a special Rayleigh projection for this kind of vector field. Okay, so we call this projection operator to be P. Then we can define this operator B and the dual operator B prime, and the operator L here is also diagonal. Yeah, it's diagonal. So the left upper entry is identity, and the right bottom entry is the L. So this L is a very important operator. So we load it here. So the operator L is of the following form. So let me highlight this operator. Okay, so yeah, so this operator L, you see it has 3 terms. The first 2 terms is a sort of the Laplacian for the magnetic field, magnetic potential, and that's a potential function, f of r. So f of r has the following explicit form. Okay, it has several terms. Yeah, you see, it has these several terms. Okay, now after we introduce this Hamiltonian structure, now let me introduce a pretty general theory for this kind of a separable Hamiltonian system. So this is studied in another paper I wrote with my colleague Chun Zhang. We actually developed this thing for the stability of non-rotating stars of an Euler boson system. Is for a totally different problem, but somehow it turned out these 2 problems share the same Hamiltonian structure, similar Hamiltonian structure. So in the paper with Zhang, we have studied this kind of a general separable Hamiltonian system. So yeah, if you have a separable Hamiltonian system like this, now we make a few assumptions. So here the operator B in the anti-symmetrical part, for the symplectic part, this operator B is quite an arbitrarily densely defined closed operator. It could be a bounded, unbounded operator, and this B could have an infinite dimensional kernel. And for the symmetrical part, it's diagonal. And for the L, for the first block L, it satisfies a condition. We can decompose the quadratic form of L into the negative space, the kernel space, and the positive space. So here the most important assumption we made is the number of the negative directions is finite. So in other words, the quadratic form of L has only finitely many negative directions. So this is the most important assumption. And for the second diagonal entry, A is a non-negative operator. So it has no negative directions. Then we have a general theory for this kind of a separable Hamiltonian system. So one of the conclusions is for this kind of a separable Hamiltonian system, the number of unstable modes is equal to the number of negative modes of L restricted to the range space of B taking closure. Okay, so in other words, we can reduce the study of this linearized equation. If you want to find the eigenvalue of this kind of linearized problem, you can equivalently study the problem to find the number of negative directions of the quadratic form of L restricted to a subspace, the range space of B. Okay, so so somehow, yeah, it becomes a much easier problem to study. Okay, so this is one of the main conclusions for this kind of general Hamiltonian system. Okay, now let's go back to the MHD problem. So if we have written a linearized MHD equation as a separable Hamiltonian system, now we can try to compute this number, right? We can compute this number. Okay, so first let's try to see what's the closure of the range space of B. So it turned out it has a very simple characterization. So the closure of the range space of B is actually the functions with no zero modes. In other words, if you do the Fourier expansion, because for the z direction is periodic, so you can do the Fourier expansion in the z variable, right? Let's say you expand the gi by the Fourier expansion, I equal to now let's use another index for the summation. Say H. Yeah, if you do the Fourier series expansion, now the condition is simply the zero mode H0 should be equal to 0. Okay, so this is the condition for a function in the closure of the range space. Yeah, the function has two entries, G1, G2. So each entry has to have no zero mode in order to be in the range space of B. So you can find it out. Then it becomes quite easy to study the number of negative modes of the projective form of L restricted to this subspace, because now we can do the Fourier expansion. Okay, we do the Fourier expansion. Now it turns out the projective form of L is diagonal in the following sense. It's diagonal. So for if you look at each of the Fourier component, the operator is reduced to a ODE operator. This number 18, right? Indexed by K. Okay, now we can draw the following conclusion. So the number of unstable modes for a MHD system is given by the following summation. For K equal to 1 to infinity, M minus LK. Okay, now so LK is this kind of ODE operator, and this ODE operator only differed by K. So K is from 1 to 3, so on and so forth. Okay, so if you look for the unstable modes, if you look for the negative eigenvalues of this operator LK, you only need to look at K equal to 1, right? If for K equal to 1, there's no negative eigenvalue. Then for any K greater or equal than 1, or greater than 1, there's also no eigenvalue, right? No negative eigenvalue. Because if K is larger, then you have the relation, right? LK is greater than L1 for any K greater or equal than 2. So eventually, the linear stability condition is reduced to check a ODE operator L1 has no negative eigenvalue, right? So this is the sharp linear stability condition we end up with, right? So you only need to look at this kind of ODE operator for K equal to 1 to see whether or not you have a negative eigenvalue, right? If there's no negative eigenvalue, then for the MHD problem is linearly stable. And if there's a negative eigenvalue, then it must be unstable. And you can also find the number of unstable modes by adding all the negative eigenvalues of the operator LK, right? And this summation is a finite summation, because if K is large enough, there cannot be any negative eigenvalue, right? If K is large, then this term is the dominant. This term is dominant. Yeah, this term will be too positive to disallow any negative eigenvalue. Okay. Okay, so this is the conclusion we can get from the general separable Hamiltonian system. Now let's try to get a more explicit criterion from this condition L1 to be greater or equal to 0. But before doing that, let me also mention, if you have this kind of a separable Hamiltonian system, we can actually get more than this number of unstable modes. It can also give you a invariant decomposition for your semigroup. Yeah, this is very useful when you study the nonlinear problem. So we can decompose our function space into 3 invariant subspace: the unstable space, the stable space, and the center space. So here we have the so-called exponential trichotomy associated with these 3 invariant subspaces. Basically, on a stable space, you have an exponential decay in a positive time direction. For the unstable space, you have the exponential decay in the negative time direction. And on the center space, you only have a polynomial growth. Okay, so this is the exponential trichotomy. Okay, now let's get some corollaries from the linear stability condition. Okay, so we can get the following corollary. If you look at the limit, epsilon goes 0. So yeah, this is the case treated in the astrophysics literature, right? You take the limit of a small magnetic field. Now you can get from our stability condition the following corollary. If you take a epsilon go to 0, in this limit, the necessary and the sufficient condition for instability is exactly the MRI criterion. In other words, is partial R omega square should be positive everywhere. Okay, so this is a sharp condition for linear stability in the limit epsilon go to 0. Yeah, if you look at our operator error, you can see very clearly why this is the case. So the operator error 1 is this part for k equal 1 plus a potential function fr. So fr is written here. So if you look at this function fr, you can see the epsilon only show up in the first term, right? The epsilon only show up in this term. The other 2 terms does not depend on epsilon. So if you look at the limit epsilon tend to 0, actually the first term gonna be the dominant term. So if partial R omega square can take a negative value at any point, then when epsilon is big, the first term gonna becomes very negative. So this tell you can get a negative eigenvalue for the operator L1, so you get the instability. On the other hand, if partial R omega square is positive everywhere, then the first term will becomes very positive when epsilon is epsilon is small. So this will dominate over the other 2 terms. So in other words, you cannot get any negative eigenvalue, then you get a linear stability, right? So it's very, very easy to see from the form of this potential function. Okay. So this is the first corollary. And secondly, you can also get a stretch code for the magnetic field for linear stability or linear instability. So in particular, if you take a B to be equal to constant, in other words, for the uniform magnetic field, then upper bound B0 is defined. We have a relational characterization of this stretch code magnetic field. So for linear stability, the magnetic field, the strength of the magnetic field has to have a lower bound. It has to greater than this stretch code. Okay, if B is equal to 1, epsilon has to be greater or equal than this stretch code B0. So in other words, for epsilon less than B0 is unstable, but for epsilon greater or equal than B0 is stable. In other words, if the magnetic field is large enough, then it becomes stable. Okay, so we get a stretch code for the magnetic field strength. Okay, now let's see. Now let's make a few comments. So we can see if epsilon tends to 0, the MRI criterion does not go to the Rayleigh criterion for epsilon equals 0. So this is a singular limit. And if you compare the two cases, you can see there's some other fundamental differences. So first, if you use this kind of a Hamiltonian structure, now you can see all the unstable spectrums are discrete. Actually, the spectrum is going to be like the following. So you have a unstable eigenvalue, unstable and stable eigenvalue are discrete spectrum on the real axis. And for the imaginary axis, you might have the continuous spectrum, but there's no spectrum like here. It's impossible to have this kind of a complex eigenvalue. Okay, so everything outside the imaginary axis, beyond the imaginary axis, is a discrete spectrum. Okay, and also we can see from our stability criterion. So the unstable mode is associated with the low frequency, right? Because if K is big, there's no instability, right? If K is big, then error K is positive, there's no instability. If error K is positive operator, then there's no unstable modes for the free K. Okay, so for MHD system, we know the unstable mode is a discrete spectrum and is associated with the low frequency. Okay, but if you compare the Euler equation for the rotating flow, satisfying the 3D Euler equation, we can see the most unstable eigenvalue is obtained at the high frequency limit. So in other words, if you want to get the most unstable mode, your frequency has to go to infinity. And also the instability actually is if the Rayleigh condition is not satisfied. In other words, if the momentum square is not monotone, then for each frequency, you have an unstable mode. So if you let the frequency go to infinity, actually you'll get the continuous spectrum due to this accumulation of high frequency unstable modes. So you can see there's fundamental differences between these two cases. For MHD system, the instability is discrete spectrum and the low frequency, but for the Euler equation is a high frequency and is a continuous spectrum. Okay. Okay. Now let me talk briefly how to go from the linear stability and the linear instability to the nonlinear dynamics. First, let's talk about nonlinear stability. For the nonlinear stability, we use the so-called energy Casimir method. So, first let's indicate for the nonlinear MHD system. Besides the energy, is a conservation. The energy is a conserved quantity. The total energy is conserved. There's infinitely many invariant quantities given by the following two. So first, if you take any function of f, the integral of f of psi is invariant. So psi is the magnetic potential. And the other invariant quantity is if you take the function capital phi, then r v theta times capital phi of psi, this is also invariant. Okay. So there's infinitely many invariants because this f and the capital phi can take any function. Okay. So by using this invariance, so we can construct a energy Casimir functional. So the functional has two parts. The first part is the energy, total energy, the kinetic energy plus the magnetic energy. Okay. Yeah, so these three terms add up to the h square. Okay, the total magnetic energy. And these two terms come from the Casimir invariance. So we can choose this F and a capital Phi such that the first order relation is equal to 0. So this F and the Phi are determined by the steady state. Okay. Then you do the Taylor expansion of this energy Casimir function around the steady state. Okay. So the first relation is equal to 0. And for the second relation, so after some algebra, actually we find out if you regroup, if you do some completion of square and regroup the expression of the second order relation, actually you can see it actually recover the symmetrical part of the Hamiltonian, a linear Hamiltonian structure. So this quadratic form is exactly the quadratic form associated with this linear Hamiltonian system. So somehow here we establish a relation of the nonlinear Hamiltonian function, a nonlinear energy Casimir function with this linear Hamiltonian structure. Okay. Okay, now if you want to prove stability, so let's assume the stability condition L1 is strictly positive. So we know this is the sharp condition for linear stability, right? So we assume L1 is strictly positive. So remember the sharp condition for linear stability is L1 to be greater or equal to 0. So here let's assume it's strictly positive because L1 if L1 has a 0 eigenvalue, this is sort of bottom line between stability and instability. So if you assume L1 is strictly positive, then you can hope to prove this second order relation is actually positive definite, right? If this is the case, then you get a nonlinear stability. But actually, it's not true. So if you look at this quadratic form from the Taylor expansion of the energy Casimir functional, the linear stability condition does not imply this quadratic form from 27 is a positive definite, because so the problem comes from the 0 mode. So remember, to get the linear stability condition, let's go back. So it comes from this condition, right? So L restricted to the range space of B is greater or equal to 0. So the range space of B contains the functions with no 0 modes. So in other words, if you assume the linear stability conditions, it only tell you for the non-zero modes is actually positive definite, but for the 0 modes, there's no control by using the linear stability conditions. So we need to do a little more. So to handle the 0 modes, so we need to use the infinitely many Casimir invariants to restrict the perturbations. The idea is very simple. So you find out all the negative direction and the 0 directions of the operator L0 restricted to the 0 modes. So this is a OD operator. So it has finitely many negative direction and at the most 1 0 directions. So for each of these negative or 0 directions, we can construct a invariant functional. So the invariant is Fi of psi. Fi is determined by the negative direction or 0 direction for the 0 mode. Then you can use this this additional invariant to restrict your perturbation, because your because this additional invariant will have a restriction on the perturbation of the magnetic potential. So in particular, it implies the projection of your perturbation to the negative direction or the 0 direction for the 0 mode is actually of the same order of the distance function. Okay. Then when we do the estimate of this quadratic form from the second order variation of the energy Casimir functional. So we can separate the perturbation into the negative and the zero directions associated with the zero modes. And for the other directions, by using the linear stability condition, we actually get the positivity. Okay, so for the better directions, because we have the control of the projection is of the same order of the distance, then when you do the expansion of a quadratic form, it becomes a square, right? So it becomes higher order quantity. Okay, so that's why you can treat it as a higher order quantity, higher order small quantity. Then by using the linear stability condition, we get the positivity for the other part, right? Yeah, basically, if you project away those better directions, then you have a positivity control, right? So this, yeah, if you add this together, we can get the nonlinear stability from the linear stability condition, L1 to be strictly positive. So this is for the nonlinear stability part. And for the nonlinear instability, we can also go from linear stability to prove nonlinear instability. So here, let me just show you one piece of the argument in the proof of nonlinear instability. So the proof is to perturb along the most unstable eigenfunction direction. Then try to prove this perturbed solution. We have exponential growth as long as it remain inside remain in a small neighborhood or a steady solution. So that means it will grow out of this neighborhood exponentially fast, right? Because if it stay inside the neighborhood of the steady state, the linear dynamics is dominant. So you have exponential growth along this unstable direction. So in other words, you're gonna quickly exit this neighborhood of the steady state. Okay, so in order to prove this thing, we use the approach of Grenier. So he constructed. So the approach is to construct a higher order approximate solutions. You try to make the error term to be of a higher order, because for the MHD problem, the nonlinear term has the loss of derivative, right? It comes from the various terms, like for any fluid equation, we know like this convection term. If you linearize it, the nonlinear term will have a loss of derivatives. Okay, so so this approach is to construct a higher order approximate solutions to high enough order. Then you use the energy estimate to close the error term. Okay, so roughly speaking, is the very rough idea. Okay, so for one important step is to construct those higher order approximate solutions. So and for this construction, one important step is to get a semigroup estimate. So you need to show for the linearized MHD equation, it has a the solution has such a growth control. So here, capital lambda is the most unstable eigenvalue. So we need to show the solution of the linearized MHD equation has a growth exactly controlled by E capital lambda T, right? So in order to show this growth estimate, so we actually use the Hamiltonian structure. So first, if there's no derivative, so the growth estimate actually follows from the Hamiltonian structure. Actually, we have a exponential trichotomy is stronger than this growth, upper bound growth. It actually give you this upper bound growth. Okay, now how do we get the estimate in the HS space? So here we need to take X to be very large. So how do you get the estimate on the derivatives? So if you look at the z derivatives, it is okay, because if you take a z derivative, any number of z derivatives of the Hamiltonian form of the linearized MHD equation, you still get the Hamiltonian structure, because the z derivative is exchangeable with this linear operator. So you still get the gross estimate for the z derivative from the Hamiltonian structure. Now for the r derivative is not exchangeable with this linear operator, because you can see this linear operator contains the Rayleigh projection. So for the r derivative, is not commutatable with the Rayleigh projection, right, for one thing. So here we actually observe, even if you cannot use the Hamiltonian structure, but there's some other structure you can use. For example, you can do the r derivative u theta and the b theta first. Then for these two, the linearized to the linear equation is given by a anti-self-joint operator A1. So A1 is a anti-self-joint operator plus some other terms which has already been controlled. For example, like a z derivative or without any derivative. Those things we already controlled by using the Hamiltonian structure. Okay, so then for this kind of anti-self-joint operator like A1, by the Stone theorem, the semigroup has no growth. So that's why by Duhamel, you also get the growth estimate for partial r u theta and partial r b theta. And for the other four r derivatives, we observe they also have a similar structure. This A2 is also a anti-self-joint operator. So again, by the Stone theorem, and by using the already established the growth estimate for partial r u theta, then we can get the growth estimate for the r derivative for any order. So you just repeat you're just doing these things repeatedly. Then eventually we can prove for the linearized MHD equation in any HS space, you do have the desirable upper bound growth. So it's controlled by exponential lambda t. The lambda is the maximal growth rate from the linearized equation. Okay, so yeah, I think this is the most things I want to say. So of course, there's a bunch of other problems we are trying to do in the future. For example, can we do the MHD for more general magnetic field? So here we only treated a vertical magnetic field, but of course, your magnetic field can also have other components. Can we study this kind of more general magnetic field? And also we're trying to do this for compressible models, especially for modeling the rotating magnetic stars. Okay, and also here we get the nonlinear instability from the linear instability. Pretty natural question is, can we construct the invariant manifolds around this unstable steady states? Okay, let me stop here. Thank you.
Okay, yes, thanks for the nice talk. Any questions for the speaker? So I look in the I have a naive question. Your perturbation also axisymmetric, right?
Yeah. The perturbation is also axisymmetric. Yeah, you're right.
So in other words, if we do non-axisymmetric perturbation, so what can you say?
Yeah, this is a very good question. So if let's say our steady state is stable for the axisymmetric perturbations. In other words, if our orbit L1 is positive, greater or equal to 0, right? So this is linear stable for any axisymmetric perturbations. Then of course we can ask the stability questions for general perturbations. This is a more difficult problem. So we haven't done this. But I think this is a very natural question to study next. But if it's already unstable for the axis-symmetrical perturbations, of course, you don't need to look at a non-axis
right. That's true.
But if it's axis-symmetrically, if it's stable under axis-symmetrical perturbations, of course, the next step is to look at the non-axis symmetrical perturbations. Yeah, that'd be a very interesting problem to look at in the future.
Yeah, thanks. Any other question for Zhiwu? Any other questions? Okay, so if no more questions, let's thank the speaker again for a very nice talk.